Hello, my name is Darragh Murphy, and this is a presentation on the research that I conducted for my PhD work, which was investigations into the use of some nature-based solutions, some features to help to attenuate flooding risk, and improve water quality on a farm in County Cork. So you can see the study site is indicated by this little red dot here. It's on an unnamed stream in the Glashgarth catchment, which is a subcatchment of the River Lee. You can see it flowing into the River Lee there, and the impounded River Lee upstream of the Inniscarra Dam. Upstream of this farm there is predominantly just agriculture. There's a little bit of forestry and some upland heath at the headwaters of the stream, but it's a first order stream, so it's very small, relatively manageable, but it can carry a lot of water. So the study took place on this mixed use farm, which has cattle and sheep and some mixed deciduous woodland plantations, some arable pasture, arable land, and we wanted to see how we could install these measures that would help to improve water quality, help to mitigate flood risk, while ensuring that the everyday working of the farm was going to continue. So there was a flood detention basin, which was a field that was able to accommodate water directed from a stream during high flow events, so that water could be stored in the field to help to cut off the top of that flood peak as water moved down through the catchment. So the flood detention basin would have had water quality as well as hydrological effects, in that nutrients that were entrained in this water that was moving in could undergo physical retention and biological processing by the soil microbial communities. The low head weirs then were installed to see whether simple amendments to streams may help to improve water quality by, again, enhancing the contact between the nutrients in the water and reactive surfaces on the stream bed, and the microbial communities that live there. Leaky dams were installed to help to hold back the flux of water during flood peak events. We'll go into that in detail. And then we had a runoff treatment swale in a little piece of planted woodland, which was a little drain that was amended to help to mop up organic runoff from the adjacent areas. So first of all, the flood detention basin, we investigated the hydrological impact, the water quality impact, and then to ensure, or to illustrate how the nature-based solution was helping to manage these pressures, as well as maintaining the farming. Investigated the soil health and soil quality in the field. So just a quick overview of how this worked. During high flows, water would pass through this sluice here. I don't know, can you see if I got a little pointer? A little pointer. That's kind of a pointer, is it? Maybe it's red. Okay, so water moved through this sluice here from the stream during high flow events. It would flow down over the surface of the field, and it would be impounded then against this bund, this raised earthen bund here at the bottom, and then it would be retained in there until the flood peak in the stream had passed, and then it would slowly drain back into the stream through these pipes, and things would go back to normal. Within these enclosures here, we have the pieces of grass that were sampled in the flooded region and the non-flooded part of the field. So here's what would happen. You have a dry field, and then a rain event comes. You got your rain coming up here. You got a rain peak, as it were, which brings along an in-stream flood peak. So that's the upstream discharge in the red and downstream discharge in the blue. So as water is directed from the stream to the field, it creates this difference in the upstream and downstream flood peak. So essentially, the difference between the upstream and downstream is the volume of water that's being captured in this field. And then the black line here shows an estimated volume that is being held in the field, and you can see that it slowly releases water back into the system, much slower than the period it takes for the water to move through the stream. So that's attenuation. And then water goes back out to the stream and the field is dry again and cattle can continue grazing. And this is what we saw. There were 15 flood events between March 21 and January 2023. There were single peak events, multi-peak events, and there was fairly consistent attenuation of flood peaks through reducing the absolute discharge, the upstream downstream discharge, and as well as that helping to elongate the duration of the flood peak. So it worked during single peak events and during multi-peak events, but multi-peak events, as you can imagine, were a little bit trickier to manage because you have to make sure that there is sufficient storage created in the field between flood peaks if you're going to get viable attenuation. So that's very tricky to during a flood event try to figure out the right discharge in order to get to get the water into the field and out of the field, so that you can have attenuation of a given flood peak, emptying of the water from the field between that flood peak and the next flood peak, so that you have sufficient storage for the next one. In terms of water quality, there was significant attenuation of concentrations of suspended solids and nitrate across all of these sampling events. But there was significant increase in all cases, really, of phosphorus. So the concentrations of phosphorus that came in were lower than the concentrations of phosphorus that went out from the field. And as you can see, while there was significant attenuation of suspended solids, overall it was quite variable. So anything that's below the line here is production, anything that's above the line is attenuation. It's a reduction in downstream concentrations. So it was variable. It was variable among events, it was variable even within events. Depending on when you sample within the flood peak, you might get different changes. Sword health, I'll just briefly take you through this here. So we have across the season, so from July through the winter into July again, you have a reduction in the biomass of the grass, and that's sampled over winter, and then it picks back up again in the growing season, and that's typical across the whole the ponding and non-ponding zones. But there was a lower biomass produced in the ponding zone during winter when you had the most intensive flooding, but there was higher biomass in the summer. And you can see in the chlorophyll then that the which is proxy essentially for the health of the grass. It's to do with the photosynthetic efficiency of the grass. That in the ponding zone during the period of really intensive flooding, you do have some depression in the production of chlorophyll, but it picks up again during the grazing season from March onwards. You're not getting any difference between the flooding and non-flooding zones in terms of the quality of the grass that's available to the cattle that's foraging on the grass. So overall, there was no effect. I mean, there was kind of minor effects, but there was nothing significant, except for in the case of chlorophyll, there was much lower chlorophyll production during the winter. But there are no cattle out there in the winter anyway, and by the time they are back to the pasture, chlorophyll and biomass are back up to really good levels. And the soil diversity, the species of grass that the cattle are foraging on, didn't change as a result of flooding. Soil analysis showed that before and after, so 2021 and 2022, before and after flood events, there was no change throughout the field. The dry zone, the ponding zone, and the swale, which is the region of the water that of the field that the water passes over on the way to the ponding zone, they were more or less the same before and after about 8 or 10 flood events between 21 and 2022. But there was elevated available phosphorus in the soil, this Morgan's P here, in the ponding zone, but that wasn't that didn't change before and after the flooding. But it may indicate a reason why you get better productivity in the ponding zone during the summer months, although the phosphorus levels in the soil throughout the field are pretty high, so it's unlikely that phosphorus was limiting. But further research on that would be welcome. So the low-head boulder weirs then were installed to help to I can't go back. Okay, help to improve the capacity for the stream to uptake nutrients by holding water back in the system and allowing it to infiltrate into the stream bed and be in contact with microbial communities that can help to metabolize some of those nutrients that are moving through the system. And in agricultural catchments, you have straightened streams, straightened channels that are denuded of boulders, denuded of the riffle beds, and other features that help to drive water into the stream bed. So it was hoped that by putting features in that would help to get those processes going, we would have improvements in water quality. So this was tested by performing tracer solutions, where a tracer solution is poured at the upstream part of this reach here, and that causes a spike in electrical conductivity, for example, and you can track then between the upstream and downstream how the electrical conductivity of the stream is changing before and after you put the weirs in, and that can give you information about how nutrients and solutes are being held back or transformed within the system, and you can get a number of different metrics that help to describe that. So these red arrows show here how the boulder weirs help to drive water into the stream bed and potentially just bring those nutrients in contact with the soil bed for longer. But the results showed that the weirs did not promote storage of nutrients or conservative solutes within the stream. But they did show that as stream discharges increased, the weirs might have helped to hold back that water for longer, so it might have a flood management benefit in that sense. A potential reason for the boulder weirs not bringing about improvements in water quality might be that the upstream section of each boulder weir brought about deposition of suspended solids, particular organic matter that may have blocked the movement of water into the stream bed. And then in the faster moving water downstream of each weir, there was scour of the gravels, and these are the gravels that were presumably helping to bring about these nutrient changes in the system before we had put the weirs in. But the scour of those gravels then may have reduced the efficacy of the system from mopping up dissolved nutrients. Downstream of that, we have a leaky dam section. So we can see along this section of the stream here, there's a boulder weir section upstream of the leaky dam section, 4 boulder weirs, 4 leaky dams, and the leaky dams were installed above the stream bed, so that during low flows, water will flow underneath the leaky dams, and only then during high flows would water be backed up against the leaky dams and retarded within the system. So the reason for putting leaky dams in is that in less altered stream systems, woody debris is present just because it just happens naturally. If riparian trees are there, they drop branches, they fall down, and they bit by bit block up, they just kind of they affect the way that water flows down through the system. So woody debris has been removed from a lot of these channels, so they can be better managed for human activities, but that may cause water to move down through the system much more quickly. So we installed leak dams to see could we help to hold back water during these flood events, and then compared the hydrographs of high flow events before and after leaky dams installation to see did they have an effect. So leaky dams are installed to help to kind of keep the flood peak back in the system in a particular part of the catchment for longer as it moves down, essentially slowing the movement of the flood peak. But the leaky dams, there was no detection that there was an effect of the leaky dams on the velocity of these flood peaks as they move down through this part of the stream. But there was an indication that they helped to reduce the peak discharge, so the maximum discharge that occurred during flood peaks. The leaky dams helped to reduce it a bit, presumably through storage within the channel, possibly through increasing the flow path length of water as it moved down through the system as water was having to navigate around these leaky dams. But there was no evidence that they caused these flood peaks to be extended. There was evidence that they caused flood peaks to be flattened but not extended. as has been shown in some other studies. This red dotted line here shows the discharge at which the leaky dams were calculated to have interacted with the water as the water levels rise during the flood peaks. On the y-axis here, you see the discharge, and the x-axis is time. So you can see all these flood peaks. Flood peaks in natural systems are highly variable. You have big flood peaks, small flood peaks, multi-peak events. You have small flood peaks embedded within larger flood peaks. And it seems that installing some leaky dams was not really enough to reckon with the force of these real life flood events. So it was important from our perspective that we were able to present real world evidence for how these leaky dams might work in flood events. So it just these plots help to illustrate just how variable a natural flood event is. But an important finding from the leaky dams was that they caused stream bed scour and bank scour as water was backed up against the leaky dams. You can see in these red arrows here are pointing at locations in the stream channel where water is being forced to move down as it's backed up against the leaky dams. And there was evidence of bank scour where the water was not able to go underneath or over the leaky dams and instead had to erode around the edges, and that will have consequences if they're to be applied in areas where you have roads running along the side of leaky dams, or you have downstream structures that are presumably going to be affected by these scour and deposition processes. And then as the scour proceeds, the platform that is helping to hold the leaky dam in place, like the stream bed and the stream bank that the leaky dams are pinned into, that erodes. So the leaky dams then slip because they have nothing to keep them in their place. So during storm, about 2 leaky dams did slip downstream. So these were undesirable results, but they are presumably inherent to the way the leaky dams work because they hold water back in the system, and therefore they're going to create pressure differentials upstream and downstream that are going to induce bed scour, erosion, deposition processes that may not be desirable in catchments where human infrastructure like roads and bridges and that kind of thing are nearby. So if you put something in the stream, you have to accept that it's going to change the way water flows, and that's going to change the morphology of your channel. It's going to cause lateral and vertical changes in the way that water moves down through the catchment. So try to get through this now quickly. This is the runoff swale where we tried to mop up some of the organic pollution that was imprinted in the water moving down through a simple farm drain, a typical open drain that was intermittently receiving some runoff from adjacent trackways, fields, hard standings, areas that cattle frequently move along. So high loadings of organic nutrients in water will cause dissolved oxygen levels to go down as heterotrophic bacteria try to gobble up all those nutrients. They use up oxygen in the process, and if you have too many nutrients, you often have loads of nutrients and no oxygen left to help to spur on these nutrient uptake processes, and then you have big dumpings of nutrients that are essentially unprocessed into streams. So if we could help to increase the surface area available for nutrient uptake and increase the surface area available for diffusion of oxygen into the water, it was presumed that we would get an improvement in the water quality at the lower end of this treatment swale. So I installed baffles that would help to retain the water in within this broadened drain, this swale, for longer as water would move over the baffles 1, 2, 3, 4 down all through the swale. And the drain went from being narrow and deep to being wide and shallow to facilitate processes of aerobic metabolism, ultraviolet breakdown of organic compounds, and the development of biomass that would help to engender more complex nutrient processes in the system. So the broad swale and the narrow drain brought about some very different changes, effects in dissolved oxygen in particular as water moved down from cells. You get a cell like 1 to 9 there. So you have the top cell, water moves down from one to the next, and as water moves down, you're getting essentially constant um, promotion of enhancement of dissolved oxygen in the water column in the broad swale, but not in the narrow one. There was a significant attenuation of nitrate in the broad swale, but not in the narrow one. But then for the other nutrients like DOC, dissolved organic carbon, ammonia, soluble reactive phosphorus, it was highly variable. Across events, it was variable even within one event. You were getting different changes as the water moved down through it. But it was clear from the results that the narrow and broad drains brought about different kinds of effects on water quality. Some of these effects, though, were kind of overwhelmed by environmental factors like the discharge of water moving down through the drain and the inlet concentration. So you can see this is a little box of results here from the thesis where the percentage removal efficiency, so that's the difference between the upstream and downstream concentrations as a percentage, was influenced by discharge Q. So at higher discharges, you're getting lower removal efficiency. And also at higher inlet concentrations, removal efficiency goes down for DOC, but it wasn't really detectable for the other compounds. So over the whole study, it was clear that by moving water down through these broad swales, this broad swale system, we're getting increases in SRP, soluble reactive phosphorus, and in DOC, but helping to improve the concentrations of dissolved oxygen and mop up some nitrate concentrations. But excuse me. Another one. But discharge and initial concentrations may have had more pronounced effects on how these changes were going on. As you can see, the removal efficiency was very, very variable throughout the sampling. So it's not enough simply to just change the morphology of these streams. You have to reckon with seasonal changes in flow discharge, like how quickly all that water, how much water is moving down through the system, and the fact that you're going to get different kinds of nutrient loadings at different times of year. So yeah, but overall it does seem that helping to hold water back in the system for longer is good, because you're just improving the amount of time, enhancing the amount of time that's available for some quite complex nutrient processes to go on, and you're improving you're just creating more surface area for physical deposition of these particulates, so that you can go back every couple of years, maybe strip the soil away, and then you can kind of start again. And if you put it high enough in the catchment away from a stream, you're helping to protect any downstream areas from these pollutants. So overall, findings were that while some of these amendments can bring about some really positive effects, they might simultaneously bring about negative effects in terms of flood risk, water quality, bank erosion. All these things are happening at the same time. They're very complex processes going on, especially in terms of water quality, because conditions that might help to mop up a certain water quality issue, like high nitrate loadings, that might also help cause the production of other components of organic or agricultural runoff, like phosphorus. So you need low oxygen conditions to help to bring about better denitrification, but those low oxygen conditions can also help to release phosphorus that's been bound to soil particles back into the water. So because there are so many problems in these catchments, it's important to try to weigh up all the different processes that are going on. But except for the erosion that we saw with the leaky dams, the other things that we put in didn't really we didn't sense any risk of putting them in, or any negative effects on the farming practices that were there going on. But it's very important, I feel, from the work that we've done, that we're as cognizant as we can be of the variable effects that can be brought about by changing the way water flows in these systems. It's good to hold water back, but holding water back causes erosion, because you're just changing the differentials in pressure through the system. So you have to account for that. But that